Hey, how you doing?
Good, how are you?
I'm doing good.
Can the people on Zoom hear me and see the screen?
Yes.
Can the people on Zoom hear me and see the screen? Okay, thanks. Did your mask match your shirt?
They're all flannel, yeah. I think the same design would be really cool, but they're just both flannel.
Okay, I'm not as impressed then.
Fair. Sometimes a little bit of flannel is good. Sometimes. if you had to eat one element for the rest of your life, let's just say they're all edible right now, which element would you eat?
Carbon.
Good answer. That's a really good answer, I'm filling out.
How about you?
Titanium.
Why is that?
I was thinking like my teeth would be shiny then.
Be kind of stiff though.
Hey, little crunch bar.
Was it the second Terminator movie?
Oh, that he's made of it?
Yeah.
Yeah, okay, so I haven't watched it, but probably.
You haven't watched it?
No, I haven't seen Terminator.
You haven't either? Did you see the first one?
Oh, I'm sorry. If you put any Terminator like questions on the quiz, I will fail.
Our educational system is crumbling. All right, I'm gonna go ahead and start. I don't think there's really a point to it now after hearing that, but. All right, we'll go ahead and get started. We'll go ahead and get started. What we're going to do today is we're going to finish up chapter 19, the thermodynamics chapter, and then we'll start on chapter 20, which is an electrochemistry chapter. I want to remind everyone that on Tuesday, so that's this coming Tuesday, April 6th, we'll have quiz number 4, and that'll cover chapter 19. So on Tuesday, the way that'll work is we'll have a little bit of a lecture on the continuing on the electrochemistry stuff at the beginning of class, and then maybe at 20 minutes, 30 minutes in, I'll stop class, and then you can go onto Canvas and take the online quiz. The other thing I wanted to just mention is we're into April now, so happy April. But more importantly, that means it's the last month of the semester. And so the final for this class will be Tuesday, May 4th from 8 to 10 a.m. And that, so it'll be another online Canvas test, and that'll be posted on that Thursday morning, or excuse me, that Tuesday morning, and you'll take it then. I'll go ahead and put on Canvas the times and the days of the final so that you have that aware, but I just wanted to mention it. I'll mention it again as we get closer to the time, but I wanted to just bring that up to you for now. Okay, so last class, we were talking about the second law of thermodynamics, and we reached this point where we were about to mention what the third law is. And so we're going to pick up there, and we're going to mention what the third law of thermodynamics is, and then we're going to introduce the new term called Gibbs free energy. And Gibbs free energy is linking the delta H and the delta S together, and so we'll talk about that a little bit and what all that means. So the third law of thermodynamics simply says that the entropy of a pure crystalline substance at absolute zero is 0. And what that means is that at absolute zero, and remember absolute zero is minus 273 C. Absolute zero is 0 K. And what this means is that all the atoms or molecules at that temperature would be in what we call a perfect lattice. But in terms of thermodynamics, the significance of that means there's only one microstate. And so from a practical perspective, We're not going to do much with that information, but that's the basis for some of these other calculations that get done and things like that. And so obviously, absolute zero K temperature is not a very realistic temperature for us and what we operate in. But in terms of thermodynamics and some of the calculations, some of the relationships, it's important because it gets to that one microstate. And remember, we talked about last class that you quickly get a lot of microstates, even at the molecular level, with the vibrations and just movement and all that kind of stuff. And so in terms of thermodynamics, it's a big deal to have something that has one microstate. So that's the third law of thermodynamics. So let's move on and talk about molar entropies. So standard molar entropies designated by S naught is what we're going to be working with. And in general, those entropy values are higher for gases than liquids and solids. And the other thing is the standard molar entropies increase as molar mass increases, and it increases with the number of atoms in a molecule increase. So all that should be pretty consistent with what we've talked about in the past. Because remember, we said the gas phase, you have the most randomness, the most chaos, the most movement, however you want to think of it. And we also said as you get to bigger molecules, you get more movement because you have more bonds that can have vibrations and things like that. And we said as you have more stuff, more molar mass, you get more because you just have more things moving around and all that. So none of this information hopefully is a surprise because it's similar to what we talked about before. The first bullet point I'll just mention briefly, the reference for entropy is at 0 K. And like I said, realistically, that's not a temperature we work with. And so the values of the elements you maybe would expect to be 0. They're not 0 at 298 K. 298 K, remember, would be 25 degrees C, which is what we usually consider to be roughly room temperature. So that's why they don't turn out to be 0 for those elements, which you might expect. And it's because it's based on that one microstate, that third law of thermodynamics. Here are some values of molar entropies just to give you a feel. The thing I want to just point out on here, you can certainly go and look at the textbook, and there's more values in this table. But what I want to point out is for the S naught value, the units are joules per mole Kelvin. And so with a lot of these, sometimes they express them in joules, sometimes in kilojoules, whether we're talking about S or H or whatever. Just make sure you pay attention to the units so that you're working in the correct units. So there is a little bit of homework from this first part of the chapter I'd like you to take a look at. Here are some problems I would suggest you spend some time on. I'd like to go over one problem just to highlight a couple things. And that's question 19.23. And this question, we're told the normal boiling point of Br2 is 58.8 degrees C, and its molar enthalpy of vaporization, delta H vaporization, is 29.6 kilojoules per mole. And so we're asked, when this boils, does its entropy increase or decrease? Well, if we think about it, we're starting with a liquid that has a certain amount of entropy associated with it. We put energy into it, and now we've put it into the vapor phase, into the gas phase. We've said all along that as you go to gas phase, that's more randomness, more movement, more microstates, however you want to think of it. So in this boiling process, the entropy is going to increase. The second part of the question asks us, calculate the value of delta S when 1 mole is vaporized at this temperature. So we had a relationship where we can use heat. In this case, it's going to be delta H of vaporization, but heat divided by temperature, and the temperature is in Kelvin, that gives us a delta S value. And since we're told that there's 1 mole, that delta H of vaporization is 29.6 kilojoules per mole. We need to multiply by moles to get it just into energy, just the kilojoules, and then divide by the temperature in Kelvin. If we add 273 to 58.8, then that's 331.8 Kelvin. We do the math and we see we get a value of 0.0892 kilojoules per Kelvin, or 89.2 joules per Kelvin. So in this problem, what I want you to take away from is, as you took a material from the liquid phase to the gas phase, the entropy increased. Okay, and that's consistent with what we've been saying. And then the second part is just refreshing your memory on this formula to have an expression when you get some type of heat type of factor, in this case, delta H of vaporization, that divided by the temperature, and then taking into account how many moles of material you have. In this case, it was just 1, but then applying that to get a delta S value. Any questions about this one? Okay. I'm going to go ahead and move on to the next part. So if you recall, we calculated delta H values. So that was that heat of formations and things like that, using that data to calculate delta H values for reactions to give us a feel for how reactions behave. We can do a similar calculation for entropy. So if you think back to how you did those delta H calculations, products minus reactants, it's pretty much the same calculation, except now you're using delta S values. So what we do is, to calculate that delta S naught value, we take the individual delta S values of the products, sum those up, and then subtract from that the sum of the delta S values for the reactants. The coefficients N and M that you see in this formula represent the coefficients for the products and reactants in the balanced chemical equation. So if you think back to what we did for delta H calculations, we'd write out our balanced chemical equation, and then through that balancing, we might have some coefficients in front of some of the products or some of the reactants. If not, then it just implied that it's 1. But then when we did these calculations for the changes, then we would go and use that coefficient from the chemical reaction equation and multiply that by the individual, in that case, delta S, in this case, delta S values. In the previous delta H work would be a delta H value. We do that for each of those and sum up the product values and sum up the reactant values. So once again, if you were comfortable doing the delta H calculations, you should be comfortable doing the delta S calculation, because it's essentially the same calculation. You're just using the different values. Instead of H values, you're using S values. And we'll go through a couple of those a little bit later, but just remember, it's essentially the same calculation. So before we talked about how heat influenced reactions and things like that, and we talked earlier about that heat flow impacts whether we have a spontaneous reaction. And we also said entropy, or the randomness, impacts it as well. And so that we know that if heat goes into the system or out of the system, it changes the entropy of things. And that makes sense, because remember, we've talked about if you increase the temperature of things, it usually kind of speeds up the randomness, the chaos. If you take heat out, it's going to slow things down in terms of that. And so what we want to do now is we want to start looking at the relationship of reactions and spontaneity, not just from a delta H or heat flow perspective, but also incorporating in that randomness or that entropy. And so we're starting to incorporate in that second law of thermodynamics. So if we look at for an isothermal process, we can say delta S of the surroundings equals the heat associated with the surroundings divided by temperature. So that's similar to that equation that we used on the example problem a few moments ago. Well, the surrounding and the system are going to be equal but opposite in sign. And so then that's the opposite sign rather, and that's going to be minus Q of the system divided by temperature. If we assume constant pressure, and if you think about, if you consider atmospheric pressure essentially constant pressure, then that Q of the system is simply the delta H naught for the system. So what we can do is we can rewrite this equation, and instead of it having delta S equals Q surroundings divided by T, or delta S equal to minus Q system divided by T, we can say that it's delta S of the surroundings equals delta H of the system divided by T. The T is the temperature again. That's assuming the constant pressure. So what we're doing is we're kind of rewriting these equations in a way to get us to where it's going to give us a little more information. If we consider that the universe is composed of the system and the surroundings, and so when we say universe, we're just saying everything. And if you think about it, you have the system you're looking at, you got everything else. That's everything. That's the universe. So that delta S of the universe is going to equal whatever the delta S for the system is, plus the delta S of the surroundings. For the process to be spontaneous, the delta S needs to be greater than 0. So in other words, it has to be positive. Okay, so what we're saying is that for it to be spontaneous, we have to create some more chaos. And that's what we talked about in the previous lecture. So this, once again, this is something that we've talked about already. So now let's start working through what that means and see how we can use some of these relationships that we've defined to go ahead and get to what we see at the bottom here. It says delta G, the Gibbs free energy value, which allows us to link together the delta H and the delta S and how each of them impact spontaneity of a reaction. So we go to the top here and we go back to our delta S universe equals delta S system plus delta S surroundings. We had said we can substitute delta S surroundings for delta H system minus, rather negative delta H system divided by temperature. So we'll do that substitution. Now, here what we're going to do next to kind of rearrange things, we're going to multiply everything by minus T. If we multiply everything by minus T, now starting on the left, we have minus T times delta S universe equals minus T times delta S system. And then if we multiply minus T times minus delta H system over T, the T's cancel, the sign goes from negative to positive, and we're left with delta H system. So by doing that rearrangement, it's looking a little different, and you'll see in a moment here why we're doing that. We can then rearrange it further, and we're simply just going to switch places with the positive delta H and minus T delta S to give us minus T delta S universe equals delta H system minus T delta S of the system. delta G is a new term for us, and this is called Gibbs free energy. And what Gibbs free energy represents, it represents this minus T delta S universe. So instead of keep writing that minus T delta S universe, we're now going to write delta G, okay? And then that leads us to our final equation down here at the bottom of delta G equals delta H minus T delta S. So what that does is, it shows us, so what we're calling Gibbs free energy, it shows how that's dependent upon delta H, delta S, and then the temperature. And so now we're starting to link in both delta H and delta S as we see if things are spontaneous or not. And we'll get to how we define the spontaneous with regards to delta G here in a moment. So hopefully you understand how we worked through this and got to the final equation. If you didn't, I would suggest, taking another look at it and just kind of walking it through it again. But most importantly, remember this last term here, this last equation, which gives free energy, delta G, that delta G value is equal to delta H minus T delta S. We will use that formula for some calculations a little bit later. So what is the significance of that delta G value, that Gibbs free energy value? Well, if delta G is negative for a reaction, then that reaction is spontaneous. If it's 0, then the system's at equilibrium. If delta G is positive, the reaction is not spontaneous. The reverse reaction would be spontaneous if delta G is positive, but the reaction is written as not positive. So Gibbs free energy, and once again, Gibbs free energy is this formula at the bottom of this slide, the delta G equals delta H minus T delta S. So if that delta G value calculates out and it's negative, then the reaction is spontaneous. If it's 0, we're at equilibrium. If it's positive, then the reaction is non-spontaneous. So that's that delta G sign, negative, 0, positive, that information, knowing whether that means the reaction is spontaneous or not, or at equilibrium, you should know that. So we talked a little bit about calculating delta S. We previously had done calculations for delta H, and we said those two types of approaches were pretty much the same. Products minus reactants, you sum up the products minus the sum of the reactants. You take into account the coefficients on the balanced chemical equation. Well, we can calculate out delta G values too from using the delta G formation values. So this calculation, hopefully you see the formula here, and it looks very similar to the delta H and the delta S ones. And it's pretty much the same calculation again. You'll have these standard free energies of formation, these delta G, not Fs. And you'll look those up for the products. You'll look them up for the reactants. You'll sum up the products. You'll sum up the reactants. You'll use the stoichiometry from your chemical equations to see if there's any coefficients between any of the products or reactants. If they are, then you multiply the delta G value by that coefficient, and you do that summation. So we've got 3 types of calculations: delta G, delta H, delta S. It's kind of the same calculation. The only difference is you're using different values from a table or given to you or however you get it. But that approach here, products minus the reactants, summing up products, summing up reactants, paying attention to the balanced chemical equation so you know what the coefficients are, same idea. When those standard free energies are determined, And this is certainly not something we're going to do in this class. But when it is done, for solid material, the standard state is pure solid. For liquid, it's pure liquid. For gas, it's 1 atmosphere pressure. For solution, it's 1 molar concentration. For the element itself, it's 0 for the standard state. So that's just some definitions. I'm not going to worry too much about that, but did just want to let you know about that. Now, here's something that you should spend some time on. This is the kind of thing I would expect you to know. And what we're doing here is we're seeing how delta H and delta S affect reaction spontaneity. And it's through this Gibbs free energy relationship, delta G equals delta H minus T delta S. And remember, if delta G is negative, are we spontaneous? Yes, we are. If it's positive, we're not spontaneous. And so one of the nice things about this delta G relationship is it tells us, depending upon what delta H is and delta S is, whether our reaction can be spontaneous or not. And that's what's going on in this table. And so let's just take a look at this for a moment. The first set of minuses and pluses, we have a minus delta H and a positive delta S. So if we put that minus delta H in here into our delta G equals delta H minus T delta S equation, so then that term would be negative. If the delta S is positive, then that T delta S term is going to stay negative. And so if both of those are negative, then we know that delta G has to be negative, right? If delta G is negative, then we know it's spontaneous. So without even knowing what the numbers are, just by knowing the signs of the numbers, we know if delta H is minus, delta S is plus, then the delta G is going to be minus. And that tells us no matter what the temperature is, it's spontaneous. If we look at the next one, we have a positive delta H and a minus delta S. We plug those in, so now delta H is positive. If delta S is negative, then a negative delta S, we have a negative temperature, that's going to be positive. So now our delta G has to be positive, irregardless of the temperature. And so that tells us that for a positive delta H and a negative delta S, it's non-spontaneous at all temperatures. So we get a little bit of information just from seeing what the signs are of delta H and delta S, get a feel for if the reaction is spontaneous or not by using this Gibbs free energy equation, delta G equals delta H minus T delta S, because that helps us understand that relationship, delta H and delta S relationship in terms of spontaneity. Now, the next two are a little more complicated. We have a minus for delta H and a minus for delta S, and the last one a positive for each of those. And what you find out there is, what's the answer about whether it's spontaneous? Well, the answer is it depends. It depends on what the temperature is. And we see on the first one where they're both negative, it's spontaneous at low temperatures, but non-spontaneous at high temperatures. And then it's just the opposite for if they're both plus. It's spontaneous at high temperatures, non-spontaneous at low temperatures. Well, you're probably wondering what the heck is a high temp and what's a low temp? Well, it depends. It depends on what the delta H value and delta S value actually, what those values actually are. So you could play around with the math if you wanted to and kind of get a feel for what they're calling a low or high temp. I'm not too worried about that myself. But based on what these delta H and delta S values actually are, then that's where you kind of see at what point does the temperature make it spontaneous or non-spontaneous, each of those. So the takeaway here, a minus delta H, a positive delta S, we're going to wind up with a negative delta G. If it's negative delta G, we're spontaneous. Positive delta H, negative delta S. We wind up with a positive delta G no matter what the temperature is. That's non-spontaneous. If they're both delta H and delta S are either both positive or both negative, then it depends. Depends on what that temperature value actually is. And it depends on exactly what the delta H and delta S values are. So this is a table, like I said. Take a look at it. Make sure you're comfortable with understanding kind of the logic behind understanding if it's a positive, negative type values and how that impacts the delta G. Delta G negative is spontaneous, delta G positive. Delta G positive, non-spontaneous. Okay, any questions about this one? All right, we're gonna go to the next then. How does delta G change with temperature? Well, like I said, negative is what you want. The general takeaway is usually higher temperatures lead to spontaneity. And so hopefully that's not too different than what we've been saying all along. So now let's talk a little bit about free energy and how it relates to equilibrium. So remember, last few weeks we've been talking about equilibrium a lot. So now we're gonna incorporate that into this. And so you can find a free energy change through this formula here. Delta G equals delta G naught plus RT times the natural log of Q. So R is a constant, T is temperature, Q. Q should be familiar to you. Q is what we used when we were talking about equilibrium. Remember, if we were at equilibrium, we'd have an equilibrium constant, but we would calculate those Q values, products over divided by reactants, to tell us how close we were to equilibrium. That's the same Q, okay? It's the same idea here. So let's walk through this a little bit to get to a formula that we're going to use to do some calculations a little later. So at equilibrium, Q equals K. We also said at equilibrium that delta G equals 0, remember? And so if we go back and rewrite that equation, well, now we're substituting in 0 for that delta G value. Then we have delta G naught plus RT times the natural log of K. Because we're saying at this equilibrium point, Q and K are equal. So instead of having that Q value, we have our equilibrium constant value. We can rearrange this, okay? And now we get delta G naught equals minus RT times the natural log of K. If we take the antilog of each of them, then we have, and do a little bit of movement the minus RT over to the other side with the delta G naught. We have K equals E to the delta G naught, or the negative of that, divided by RT. So personally, I think the delta G naught equals minus RT natural log of K is a little easier one to remember than the one with the E to the whatever power. So what we have here now is we have an expression that links delta G and equilibrium constants. So we've got this relationship now. And so if delta G is negative, then K is going to be positive. The more negative delta G is, the larger K is. If delta G is positive, then K is negative. And finally, if delta G is 0, then K is 1. So this just tells us what our relationship is between delta G and K. Remember, if delta G is negative, it's spontaneous. So that's telling us also that if K is positive, it's spontaneous. So that kind of makes sense. Okay, there are some homework problems associated with this second part I'd like you to take a look at. Here they are. As usual, the homework problems are posted on Canvas if you get stuck and want to take a look at the answers. But before we move on, I want to go through a few homework problems just so that you can see an example of how to use some of the formulas and things like that. So the first one I'd like to take a look at is 19.57. So let me get that one out here. Okay, in 19.57, you're told to use the data in Appendix C to calculate delta H naught, delta S naught, and delta G naught at 298 for these following reactions. So let's take a look at a couple of these. So the first thing we always want when we do these calculations is to take a look at our balanced chemical equation. So we were given that H2 plus F2 goes to 2HF. So we see HF as the product, H2 and F2 are the reactants. And so let's calculate delta H first. So delta H is going to be the sum of each of those formation constants of the products minus the sum of the formation constants of the reactants. So we look those up in that table that they suggested. So either you'd look it up in a table or you'd be given the information. And so on the left-hand side here, we have delta H naught, then we have the sum of the products. We only have one product, so that's the HF. And so that delta H, the formation value, is minus 268.61. We see that there's a coefficient of 2 in the balanced chemical equation, so that's why we have to multiply that value by 2. That's all of the products we have. We don't have any others, so we're done with that part. Now we're going to subtract the sum of the heats of formation for the reactants. The reactants in this case, H2 and F2. We look those up in the table, and we see that in that case, this case, each of them have a value of 0. So we're done. We do the math, and we come up with delta H equals minus 537.22 kilojoules. Okay. We said before, so we're pros at doing delta H calculations. We've done those before. We said that delta S and delta G calculations are going to be pretty much a similar calculation, pretty much the same thing. So once again, we do that sum of the products minus some of the reactants for the delta S. We look up those S values. In this case, we just got to remember again our 2 for the HF for the product part. So we have 2 times its value, 173.51. And then on the reactant side, for the delta S values, we actually have numbers, it's not 0. So we got to plug those numbers in from the table, 130.58 and 202.7. We add those 2 numbers up and then subtract them from that 2 times 173.51 value. And if we do that, we get a value of 13.7 joules per kelvin. The one thing I do want to point out is note that delta S value is joules. The delta H was kilojoules. So we got to keep that stuff straight there, okay? And then finally, delta G. there's actually two ways we could calculate the delta G value. And in theory, they should be the same. Sometimes they are not, but usually they're pretty close. We can do the delta G by doing a similar calculation as we did with delta H and delta S, where we sum the products using the delta G formation values, and then subtract the sum of the reactant values. So if we do that, it's a similar exercise as the previous two. So we have 2 times that delta G formation for the HF minus the sum of the delta G values for H2 and F2. In this case, they're both 0. And so we get a value of minus 541.4 kilojoules for the delta G naught value. We also, though, could use our formula, our Gibbs free energy relationship of delta G equals delta H minus T delta S. We could do that as well because we calculated up in the first 2 parts of the problem, the delta H value and the delta S value. So we could go ahead and plug those in. We were told what the temperature was. We were told it was 298 Kelvin, so we could plug that in. The only thing that we have to be careful about on this calculation is, remember, our delta H value was kilojoules, our delta S value was joules. So if you notice down here, I have minus 537.22 kilojoules. And then for the delta H value, and then for the delta S value, I have 13.7, but I multiplied it by 10 to the minus 3 to convert that joule value into kilojoules, okay? So as long as I remember to make sure I'm working in both, either both kilojoules or both joules, doesn't matter which way you do it, but they gotta be the same, then I go ahead and do that math and I get minus 541.3 kilojoules. Pretty close, 541.3, 541.4, pretty much the same number. So in this case, they calculate out to be the same. Okay, let's take a look at another one. In B, we have graphite plus 2Cl2 going to carbon tetrachloride CCl4. Okay, well, we're going to do just like we did on the last problem. We're going to first calculate our delta H's, delta H value using the delta H of formation values for products minus reactants. The product is the carbon tet. That's 107 minus 107.6. The reactants are the carbon and the Cl2. In this case, both carbon and Cl2 have values of 0. I went ahead and put my 2 in front of the Cl2 one, just because I want to get in the habit of accounting for the stoichiometry of the chemical equation. Then the next one is go ahead and do the delta S value. So I look those formation values up. I get the value for the carbon, the CCl4, that's 309.4. And then I subtract from that the sum of the reactants. The carbon is 5.69. The Cl2 is 222.96. I'm multiplying that Cl2 value by 2 because of the stoichiometry of the chemical reaction. So that 2 in front of the Cl2 means I've got to multiply it by 2 down here. I go ahead and do that math and I solve and get my delta S value. Now I get to delta G. Just like on the previous problem, I can solve it 2 ways. One is if I have all the delta G values, formation values, I can use those. Or if I don't have those, I can use the information that I got for delta H and delta S and plug it into that Gibbs free energy formula. So let's take a look at those. Products minus some of reactants. So product minus 64.0 kilojoules per mole. The reactants both turn out to be 0 for the delta G values. And so I wind up with minus 64.0 as my delta G naught value. If I go ahead and use that Gibbs free energy equation, then I can go ahead and bring my delta H value down. That's the minus 106.7 kilojoules. Minus the temperature, 298 K, times the delta S value. That delta S value was expressed when I solved for it in joules. So I need to convert that to kilojoules by multiplying by 10 to the minus 3. So now I have kilojoules and kilojoules with my math. That's what we want. Go ahead and finish that calculation. I get minus 64.3 kilojoules. So once again, in this case, they're both pretty close. And so that's fine. Any questions on this type of calculation? The key things, just to review, you want your balanced chemical equation. That's important because you want to see what those coefficients are, because that's going to show up possibly in your calculation, depending upon what the actual values are. Then you have whether it's delta H, delta S, or delta G. You can do the product, sum of the products minus the sum of the reactants, and make sure you take into account any of those coefficients from the balanced chemical equation. You also can use that Gibbs free energy expression to solve for delta G or the other things if you have some of that information. Okay, let's take a look at 19.75. So in 19.75, we're asked whether delta G increases, decreases, or stays the same if the partial pressure of oxygen is increased. In other words, if you increase the amount of oxygen. So at the very top, I have my formula, which links delta G to equilibrium, okay? So it's delta G equals delta G naught plus RT times the natural log of Q. And remember Q, that goes back to our equilibrium type stuff we did when we were doing solution equilibrium, where that's simply concentration of the products divided by concentration of the reactants. So let's look at our first formula here. 2CO plus O2 go to 2CO2. If we write the equilibrium expression for that, we have CO2, because there's a 2 in the front, we square that, divided by CO and O2, there's a 2 in front of the CO, so we square that term. If we're saying that we're increasing oxygen, then that tells me that this O2 value in the denominator increases. If that increases, then what does it do? If something in the denominator gets bigger, then that Q value gets smaller, right? If that gets smaller, then that's ultimately going to have my delta G value decreasing. So this logic on this is really kind of the similar logic we had when we were looking at solution equilibrium. We look at the next one. We have 2H2O2 going to 2H2O, going to gas. The H2O2 and the H2O have the little L, so I've crossed those out. So basically Q equals O2 concentration. If that Q is getting bigger, then delta G's got to increase. And then finally the last one, 2ClO3 going to 2KCl plus 3O2. The two potassium compounds are solid, so I cross those out. And so once again, Q proportional to this oxygen. So if that oxygen goes up, delta G is going to increase. So what we're looking at here is we're leveraging our relationship, which relates delta G and equilibrium constant. And then we're remembering how to write our equilibrium expressions. And then we're looking to see if what we're varying is in the numerator or denominator of that expression. If it's in the numerator, it goes up, it increases the delta G. If it's in the denominator, it goes up, it's going to decrease the delta G. All right, let's look at 19.79. So in this one, we're told once again to go to Appendix C and use the data there to calculate the equilibrium constant K and delta G naught for these reactions. Okay, so let's take a look at the first one. So we always want to have that balanced chemical equation, and we have that up there. We have H2 plus I2 going to 2HI. And then to get delta G, we have that Appendix C, which has all these these formation values, so we can look those up. And so we're gonna have products, some of the products minus some of reactants. So for the delta G, we look up the HI value, it's 1.30 kilojoules per mole, and we have 2 moles of that. Then no other products, so then we move on to the reactant side, we have H2 and I2. We have 0 is the value for H2, I2 is 19.37. So then we would sum that up and subtract that from our product side, and we get a value of minus 16.77 kilojoules. Well, now we've got our delta G naught value. We still want to solve for K. And remember, we had rearranged the formulas before to have this expression delta G naught equals minus RT times the natural log of the equilibrium constant. So we've got this equilibrium constant now that we want to solve for. We know that R is the constant 8.314 joules per Kelvin. We know the temperature was 298 Kelvin. Temperature has to be in Kelvin because of this constant. We want to cancel out those Kelvin values. The other thing, though, is our delta G naught value is going to have to be in joules because our constant is in joules. When we solved up top, it was in kilojoules because that's what the values we were given out of the table were. But to use this formula, because of that, what that R value, what its units are, joules per Kelvin, we have to make sure temperature is in Kelvin, we have to make sure the other energy stuff's in joules, so things cancel out appropriately. So we take that minus 16.77 kilojoule value, multiply it by 10 to the third to convert it to joules. And so now we have that expression of minus 16.77 times 10 to the third joules equals minus 8.314 times 298 times the natural log of K. So we can go ahead and do some math there, and we get to 6.769 equals natural log of K. We take the natural antilog of that, and we get K equals e to the 6.769. So this is another chance for you to use your neglected calculator keys. So make sure you know how to do that e to the whatever calculation on your particular calculator, okay? I think everyone probably has a good handle on that by now, but just make sure you're comfortable with that. Because this is the ln, it's not the log log, so this is the natural log. That's why we're using e to the whatever power it is, in this case 6.769, rather than 10 to that. So make sure you know how to use that e to the whatever key on your calculator, and then if you do that, you get the final value of the equilibrium constant. In this case, it's I can read my handwriting. I think it's 970. Okay, let's take a look at another one of these. So in B, we have C2H5OH going to C2H4 going to water. And what we see here is the water actually has a little G. It's not the liquid. So it is something that participates in the reaction. So to find our delta G value, it's products, sum of products minus sum of reactants. So we look up those delta G values for C2H4. That's the minus 228.57. We look it up for gas phase water. That's 68.11. We add those up. And then subtract from it the reactants. In this case, it's just the methanol, which is, or the ethanol, which is C2H5OH. That value for the table is minus 168.5. So notice that this is a minus value, but it's that minus, so it works out to be a plus there. So we go ahead and solve that for kilojoules, convert it to joules by doing the 10 to the third. And then just as we did above there, we can plug things into that delta G equals minus RT times natural log of K, and then go ahead and solve for K. I'll say it again, make sure, because the constant is joules per Kelvin, make sure that that delta G value is expressed as joules. If you leave it as kilojoules, it's going to be wrong. Because you got to have those units canceled. we find ourselves with another one of these each, in this case, to the minus 3.245 equals K. We're good at our calculator now, so we're able to do that calculation and get 0.0390 equals K. The third one is a similar thing, so I'm not going to bother going through that unless someone has a real burning desire to see it or a big question about it. Okay. So that ends our chapter on thermodynamics. So once again, we'll have a quiz on Tuesday. So next class, we'll have a quiz on this, and that'll be quiz number 4. So what I'd like to do now is I'm going to pull up the electrochemistry and spend the last part of the class starting on that material. So hold on a second here. Okay, so hopefully everyone can see my slides. If not, let me know. Okay, so electrochemistry. I think the class has been doing some of this recently in lab, so hopefully this won't be totally new for you. And so what are we talking about with electrochemistry? So in electrochemistry, what we're talking about is how really electricity impacts chemical reactions. That's really as simple as it is. And so we'll be talking about oxidation, reduction, moving electrons around, things like that. And so speaking of oxidation and reduction, the most simple definition of these terms, most simple definition of these terms would be for oxidation, loss of electrons, reduction, gain of electrons. Okay, so if you hear the word oxidation, you should be thinking loss of electrons. If you hear the word reduction, you should be thinking gain of electrons. Well, you may remember last semester, we did something called oxidation numbers. Okay, so if you've forgotten it, we're going to go through a little bit of a refresher here. And if you thought you were finished with that, unfortunately, it's back. And so oxidation numbers are a way we kind of do the chemical accounting of seeing if things are being oxidized or reduced. So there are a few general guidelines that you can use in trying to figure out what oxidation numbers are. So the first is that if it's an element, the oxidation number is 0. If it's a monatomic ion, the oxidation number is the charge, okay? So if it's like Fe plus 3, then the oxidation number is plus 3. If it's Cl minus, it's minus 1. Fluorine in a compound is almost always minus 1. Oxygen in a compound is almost always minus 2. There is an exception. If it's a peroxide, it's minus 1. But other than that, it's going to be minus 2. Hydrogen is almost always plus 1, unless it's a metal hydride that is minus 1. So not a lot of guidance, but believe it or not, it's usually enough to help you figure things out. The other thing I want you to remember is the sum of the oxidation numbers has to equal the overall charge. So if it's a neutral molecule, then the sum of the oxidation numbers have to equal 0. If it's a molecule that has a plus whatever charge or minus whatever charge, then the sum of the oxidation numbers has to equal that number. So this is a pretty handy slide here to kind of refresh your memory on the oxidation number stuff. There are some homework problems on this, so it'll give you a chance to kind of refresh your oxidation number ability. I would strongly suggest that you spend a little time on that homework to make sure you're comfortable doing oxidation numbers again, because it's been a while since we did that. That was last semester, I believe. So the oxidation numbers, like I said, are kind of our accounting system, our bookkeeping system to keep track of what's losing electrons, what's gaining electrons. And that's where that oxidation number thing comes through. If the oxidation number increases, you lose electrons and the element is oxidized. If the oxidation number decreases, you gain electrons and that element is reduced. So think about if you lose electrons, then you go from, say, a neutral, a zero oxidation number to a +1 or +2 or +3. Because remember, the electrons are negatively charged, so you're removing negative stuff from it. That's why it becomes positive. And then just the opposite for gaining electrons. So we said the base definition of oxidation was loss of electrons, and the base definition of reduction was gain of electrons. There's a couple other ways to define oxidation or reduction. And oxidation can be the gain of oxygen, or it can be the loss of hydrogen, in addition to that loss of electrons. And reduction can be loss of oxygen, gain of hydrogen, in addition to that gain of electrons. So there's a few ways you can define it, oxidation, reduction, but the one thing you also need to remember is that oxidation and reduction always occur together. So in other words, you're not going to have oxidation and nothing get reduced, and vice versa. So if you've got oxidation, somewhere there's reduction. And they're always paired up. So let's talk about oxidizing and reducing agents. So oxidizing agents are things that tend to gain electrons easily, and they bring about oxidation of the other substance by being reduced themselves. So oxidizing agents are reduced during an oxidation reduction reaction. Oxidizing agents are reduced. So something that's reduced is an oxidizing agent. For me personally, I've always found this very confusing. Okay, so I always have to look at it a few times and think about it before I talk about this. Reducing agents, those are things that tend to lose electrons readily. They bring about the reduction of other substances because they're being oxidized. So something that's oxidized during an oxidation reduction reaction is a reducing agent. Something's oxidized is a reducing agent. Something that's reduced is an oxidizing agent. Hopefully you don't find this confusing. Like I said, for me, I have to think about it a little bit every time I look at it. But you do need to know that. You do need to know how an oxidizing agent and a reducing agent, how they operate. So once again, here's some examples. In this case, we have zinc. It loses 2 electrons to form zinc +2. So in this case, zinc is oxidized. And then in the other example, we have H+. It gains an electron to form H2. So that, because it's gaining that electron, the hydrogen is being reduced. And then here, this is a simple example because there's not a lot of atoms involved. But we see here on the left, we have zinc. That oxidation is 0, oxidation number 0. And then on the right-hand side, we see zinc is at +2, so now that is at +2. So it's going from an oxidation number of 0 in that metal form to the zinc +2 ion in a +2 oxidation state. So because it's lost electrons, it's oxidized. The hydrogen, we have the hydrogen ion here on the left, that's a +1 oxidation number. Over here at H2, now the oxidation number is 0. So in that case, to get from +1 to 0, it had to pick up 1 negative charge, so it picked up 1 electron. And so we say that it was reduced. The number went from +1 to 0, reduced that number. So this is a simple example because we only have a couple of atoms here. It gets a little more complicated when you have molecules that have multiple atoms and things like that, but the concept is the same. Okay, so when we talk about redox chemistry, which is what this is, we talk about oxidation reduction type chemistry. We talk about half reactions. And what we mean by the half reactions is that we write the oxidation portion of the reaction, and then we write the reduction portion of the reaction. And then eventually we combine those to have the full redox equation. But when we think about it, we treat them separately initially to kind of figure out what's going on. And so in this case here, we see an oxidation reaction of 10 + 2 going to 10 + 4 plus 2 electrons. Then we have a reduction of 2Fe + 3 plus 2 electrons going to 2Fe + 2. And so we would then go and we would balance things. So what we're going to do is we're going to take a look at this a little bit more and take a look at some of the rules that we would use to balance. So this is another one of the slides that you really need to know, okay? So balancing redox equations, I would never say that it's really hard, but you really gotta pay attention to everything. And so it's really easy to make a mistake. So the idea is I think, pretty straightforward, but how you go about executing it and making sure you don't mess up, you gotta kind of pay attention. And so this kind of flow chart here that you see on this slide, and we'll talk about, this is a really good way to go systematically through and balance these redox equations. Now, I will point out that this example here is for acidic solutions. We'll talk a little bit later about what to do with basic solutions. It's very similar, but there are some slight differences. So let's go through this. So you're given an equation and you want to balance it, and you know it's a redox equation. So the first thing you do is you make two half reactions. You split it into two half reactions. One of those is going to be an oxidation, one of them is going to be reduction. You don't know what's what yet. That's why you're going to figure out as you work through. You want to treat them separately and you want to balance them each separately. And so the first thing you do when you're trying to balance that half reaction is look at what atoms are present in the molecules and balance the atoms that are not oxygen or hydrogen. So ignore the oxygen and hydrogen initially, look for any other atoms that might be present and balance those. How do we balance? We put those coefficients in front of the molecule, right? That's our fundamental way of balancing things. Once you do that, then balance the oxygen atoms. So look at the two sides of that half reaction and see which side is deficient in oxygen. The side that's deficient in oxygen, add water atoms, or water molecules rather, to that side to get the oxygens to balance. So now you've balanced the atoms other than oxygen and hydrogen. You've balanced the oxygens. Now, obviously, when you added that water to one of the sides, you messed up the balance of the hydrogen, most likely. So what you do then is you balance the hydrogen atoms by adding H+ atoms to the side that's deficient in hydrogen. So if you go ahead and then add that to the side that's deficient, then you're going to have balanced the hydrogen. So now all the atoms should be balanced. And at this point, I would strongly recommend you look at both sides of that half reaction and count them up. Count up the non-oxygen and hydrogen atoms on each side. Make sure that balances. Count up the hydrogen and oxygen on each side. Make sure each of those balance. everything should balance. What probably will not balance, though, is the charge on the two sides, because we have to have that balance. And we balance the charge by adding electrons to one side or the other, okay? So if you add up all the charges, if you had like 2H plus, that would be +2. Then if you had some minuses and some other pluses in there, you'd add that up on each side, and maybe the total on one side is +5, and the other side is +3. What you would do is you would then balance the charge by taking 2 of those negative electrons and put it on the +5 side. And so then you'd have +3 and +3 charge on each side. So we use the electrons to balance out the charge on the two sides. So once you've got all that done, congratulations, you get to go back and do it again for the other half reaction, okay? So this is why I'm saying, there's a bunch of stuff to do, and you got to do it all twice, and you're still not done after that. So you've gone up, you've done one of your half reactions successfully, you've gone back, got the second half reaction, you've worked through this flow again, got that balance, and now what you got to do is you've got to balance the overall reaction. Well, quite often, you wind up where one of the reactions has a different number of electrons associated with it than the other one. Well, you can't have that. Those electrons have to balance out in the two reactions. So if that's the case, then the easiest way to do it is multiply each reaction by the number of electrons in the other reaction. If that's a little cloudy what that means, we'll do some examples and I think it'll be a little more clear. But that's essentially what you do. So then you have your electrons will equal. But remember, when you do that multiplication, you're not just multiplying the electrons, you're multiplying everything in that equation. So all those numbers, coefficients are going to change in each of the half reactions. Then once you do that, you add the two half reactions up. If you've got similar things on both sides of the equilibrium arrow that you can cancel out, you cancel that out. One of the things that should cancel out is the electrons. Sometimes water will cancel, sometimes hydrogen ion will cancel, things like that, but you just got to kind of see. Then hopefully everything checks out. And then what you want to do is you want to go and you want to check your work. You want to make sure that the non-oxygen and hydrogen atoms balance, the oxygen and hydrogens balance on both sides, the charge balances on both sides, all that stuff should balance. That's what I was saying before with these types of balancing equations on the redox. It's the same as when we balanced just chemical reactions before. You know when you're finished whether it's right or wrong. Because if you go back and check and everything balances, you know you're probably right. If it doesn't balance, well, you're probably wrong. So I strongly encourage you to not just wait to the end to check the balance, but kind of check when you're doing the half reactions. Each step you do, kind of just check to make sure you accomplished what you think you did. Because there's nothing more aggravating than get to the end and it doesn't balance. Because then you got to go back and sort through all this and figure out where did I make a mistake. So the other thing I'll say about balancing redox equations is that the only way that I've ever seen that you actually can get very good at them is by practicing. And so there are some homework problems associated with this. I would strongly encourage you to spend some time working through some of those so that you kind of get good at it. Because the other thing is, it's one thing to do one of these and take 20 minutes to do one. You're not going to have 20 minutes to do one of these on the exam, okay? Remember, the exam is timed, and so time is of the essence. And so you want to be able to kind of crisply go through and do the balance. Okay, so here is an example to work through that we're going to work through on balancing this reaction. We're just about out of time. There's certainly not enough time to go through this today. So we're going to stop here, but this is what we'll pick up on next week. Any questions on anything that we talked about? Okay, so I'm going to say it again just to remind everyone. On Tuesday of next week, what we're going to do is we'll have some lecture at the beginning of class, continuing on with this redox stuff. And then after that little bit of lecture, then you can go and take your quiz number 4 on chapter 19, which will cover the thermodynamic stuff. So that's it for today. Thank you.